Okay, we're ready to restart. We will now see a few more elements which are in the module called IP Part 2. There will be a Part 3. The first thing we'll discuss is address resolution, ARP. That's considered as one of the nuisances of IP and is a consequence of the history of the fact that IP is meant to interconnect local area networks. The problem that is solved by ARP is whenever an IP machine, host or router, has a packet to send to another machine that is on link. That happens because, for example, the destination is on link with you in the same LAN, or because you are a router or a host and you're forwarding to an intermediate hop. That intermediate hop has to be on link with you. In order to send to another machine that's on link, if you use a technology like Ethernet or Wi-Fi, you need something special. You need the MAC address of the destination. So, for example, whenever this has a packet to send to that, it needs to find the MAC address. And the MAC address is not present anywhere in the IP header, nor in the Ethernet header if we received it from somewhere else. So there is no way to get that information just by looking at the configuration of this router here. So we need to discover it. Remember that the MAC address is a hardware address. It's like the serial number that you have on your bicycle that is printed on the frame. Here it's a bit similar. So there is no meaning to it in particular. It's impossible to guess what this address is. The purpose of ARP, Address Resolution Protocol, is to find this address. The classical way to find it is to use a broadcast query. When you want to find an IP address and you have a name, you have a similar problem. I want to go to a server called www.epfl.ch. I need to find what is the IP address of this server. For that, I go to a server, a directory server, a DNS server. For ARP, we could have similar things. We could have a directory service inside the LAN with a map of all the MAC addresses, but this would not be very, very convenient. So we have another way of discovering an address, which we always find. There are always those two alternatives. To find an address, you can go to a directory. That means there is a well-managed book or database somewhere with all the addresses. Or you shout. You ask, who has that address? This is what ARP is doing. Of course, it works inside a room, inside a local area network. Shouting here means we will do a broadcast inside the local area network. This is illustrated in this figure. This machine has a packet to send to STI SUN1. The only thing it knows so far by analyzing the prefixes is that STI SUN1 is on link with me. So this router knows this guy is on the same local area network as one of my interfaces. I need to find its MAC address. So it will send a special packet called an ARP request, which is shown here. The ARP request in IPv4 is a very, very old stuff. It's not even an IP packet. It's a packet of its own called ARP. So when we will do Wireshark, we will find that it doesn't have an IP header. It is encapsulated in a MAC frame, of course, and the destination address is the broadcast address in the local area network. So there will be a packet sent here. Of course, it's sent to everyone. Now, everyone will receive it, and inside the ARP, there is the question, what is the MAC address of the IP address, which is here? What is the MAC address of this IP address? So there is no destination IP address because it is not an IP packet, but there is, if you want an application field, there is some data in this message, and the data is a question, who has the MAC address corresponding to the IP address that I am indicating, which is this one. So the IP address is in the message, not in an IP header. Everyone will receive it. Those three machines will receive it. If nobody is cheating, if they are not sniffers in particular, none of them will do anything because they will receive the request. They will see, oh, that's not me. And if they behave well, they will not answer anything. This one has recognized its IPv4 address in the query, not, I repeat, not in the destination header. It will send a reply to whom? Well, to the destination MAC address that is copied from the source MAC address of the query. So there was a question flow number 1 that had a source MAC address, so you will respond to that MAC address with your own source MAC address, and you will repeat in the message, here is my MAC address. At this point, this guy knows what is the MAC address that corresponds to this and can send this information. Of course, you don't do that for every packet. You do that only when it's needed, which is typically when a machine has booted or something has been restarted, because this is obviously kept in a cache. So a cache is a table, a database, where you keep information temporarily. An entry in a cache is associated with a time to live. When the time to live has expired, the entry is considered invalid. So when you do that for the first time, you keep in a cache, so this machine keeps in its ARP table the information that this address corresponds to this MAC address. And if nothing happens, if no other communication happens, after some time, the entry will become, which is, this time is typically short, a few minutes, this will start again. It will not start again if you have what we call a reconfirmation of the mapping. And a reconfirmation of the mapping is whenever this machine receives a packet from this guy. So for example, if STI Sun1 is a server that is actively being used, and this is the router, well, there's lots of packets flowing in both directions. All the packets flowing in this direction, from the host to the router, contain the source IP address and the MAC source address. So whenever this guy sees both, and if they are still the same as the ones that are in the table, you will consider that as a confirmation and will reset the timer. So that if there is traffic that is happening, you will do that only once. Once in a while, of course, you will break the link, the machine will be restarted, this one might be restarted, so you might need to do this again. This is ARP, and believe it or not, this is how it's supposed to work. I say believe it or not because it's a bit primitive, as we will see, and makes a lot of assumptions on trustability of all machines. In IPv6, there is exactly the same thing, but the names have been changed. So it's very typical of IPv6. IPv6, from all respects, is exactly the same as IPv4, except one respect. The address space is much larger, so you can do special things that you could not do with IPv4. Whenever you can manipulate the addresses, taking into account the fact that they are very large. But apart from that, everything is exactly the same, but the names are very different. So it's a pain in some sense, but we need to learn this. In particular here, ARP is not called ARP, but is a part of what is called the Neighbor Discovery Protocol, NDP, which is an application layer protocol or a management protocol that is inside IP packets. It's part of what is called ICMP in IPv4, so the control packets here. So if we do a Wireshark with IPv6, the ARP will be called differently. They will be called NDP, and they will be inside IP packets. Inside IP packets means that when we send this query, which I may continue to call an ARP request, even though formally this would be incorrect, I send it in an IP packet. Now the question is, who is the destination IP address of this packet? The destination IP address cannot be the IP address of this guy. So I'm doing IPv6. So this router here is asking who has this IPv6 address here. But of course, you cannot send it to this machine because sending it to this machine requires having the MAC address of this machine. That's what you're trying to do. So instead, you send it to what is called a group, an IPv6 multicast address. This is this address. This FF is indicative of a multicast address. So this is a multicast address, which is, we could say, everyone, but IPv6 authors tried to be smart. They don't send it to everyone. They send it to all machines that have the same last I believe 24 24 bits as this address. So you take the end of this address here. This is the IPv6 address. It's long. It overflows on 2 lines here. The end, the last 24 bits, this is 16 bits. This is 16 bits. There is a 0 here. That's implicit. So 0f are 16 bits. If you take the last, is 8 bits, sorry. If you take the last 8 bit of this word, you find 66. So the last 24 bits of this address in hexadecimal gives 66:1. You add this to a known prefix, and that gives what is called a solicited node multicast address. It's an address that is multicast and to whom should respond only the hosts that have an address that has the same last 24 bits. So the idea is that in a network there will be very few that have the same address. In IPv4 we don't do that. We send it simply to everyone and it works. Here we could do the same, but that's how it's done. So this machine, this ARP ARP request, which is part of the NDP protocol, and the name of this message is called a neighbor solicitation, is sent to this multicast address. Now, all machines here have their own IPv6 address. If by accident another of one had an address that would have the same termination, it would participate, it would listen to this multicast group, but chances are there's very few. In this case, there's only this machine. So only this one will listen to this multicast group, will receive the query, and will respond to it. And from there on, the answer will be the same here. So this is explaining how the solicited node multicast address that I've explained is done. From there on, the process is the same, with some of the details are different. The ARP reply, which is now an NDP message called a neighbor advertisement, is sent to the IP address of this guy. Now, there's no need to do subtle things because we know who sent that information. It is the source IP address of the message, source IPv6 address, and the neighbor advertisement will contain the MAC address of this guy, which is the only thing we wanted. And similarly, it will keep it in cache. So this is how ARP works. If we look inside the packets, we will see it. For example, for IPv4, we'll see an Ethernet packet and a type that says ARP. This is a symptom that ARP is seen from Ethernet, a network layer protocol. It's a special protocol. It's not IP, it's not AppleTalk, it's not DECnet. It's ARP. Now, the only protocols you see in principle inside an Ethernet are, in principle, most of the time, are IPv4 or IPv6. Here you see ARP, and then the pretty printer that has printed this trace is pre-programmed with all the fields that you find in an ARP packet. So we see that the ARP packet query contains the essential thing is what is the target IP address. This is the main thing. There's a target MAC address, which is put equal to 0. That's a constant thing you will see in low-level programming in the internet. Absence of 0 always means an absence of address. All ones mean broadcast and is not valid for a host address. 0 is also not valid and means absence of address. Typically, you use that when you prefer to have fixed format. You have a field where you need to put an address. There is no address, you put 0. You could also have a variable format and have no field here, but this is typically done there. You see that there is a lot of redundancy. I'm putting the sender MAC address. The sender MAC address is in the internet header. The source here is the same here. The sender IP address is needed because this is not an IP packet. And we see here that the query contains protocol type. Although ARP is used only for IPv4, but when ARP was invented, remember at that time, it was in the 70s, IP was an inter-networking protocol. There were other networking protocols like AppleTalk, that came a bit later, but there were DECnet, IBM SNA, Microsoft NetBEUI. So all those protocols some of those protocols could use also ARP to do the same address resolution. Today it's used only for IPv4. And an IPv6 ARP, of course, will be different. Ethernet header contains this, 86DD, which means IPv6, so it's an IPv6 packet. And we will see that the destination address in that case is the solicited node multicast address that corresponds to 011, because the target address we see ends in 011. So, given that ARP has been done, once we have the MAC addresses, a small recap question. I'm assuming here this router has a packet with a destination address, this one, which is RRC SANES, but we are here. The packet is sent to this intermediate box. This guy knows this by looking up its routing table. And now we observe this packet here at the source when it's sent by ED2IN. What is the destination MAC address that we will see? So we're observing the packet at the red circle. I close the poll in 5 seconds. And the correct answer is, of course, B. The packet is sent to the next hop, which is the router here. And this guy needs to find what is the MAC address of this router, which is this one, 9A75, which is this one here. It would not help to send to this address, because those are two distinct LANs. So if you send it to this address, it will not be reached, it will not be received by this router. And of course, same thing, it is not useful to send to the final destination address. That's important, that's one thing I keep repeating. I mean, this manipulation of which address we put at which field is really an essential way of understanding how TCP-IP works. Of course, what I've shown here assumes that everybody is behaving well. So what happens, for example, if there is an attacker that receives the ARP reply and has a very fast machine, or finds a way to slow down this machine by bugging it with pings or things like this, so that it has a good chance of being faster in responding to the ARP reply, and sends a reply with another MAC address. Then you will impersonate this. I mean, this guy will believe that this IP address corresponds to this MAC address. And there will be no way, at least no simple way, to detect that this is wrong. So you will have what is called an attack called ARP spoofing, which is very easy to mount, in particular with labs we do now. And most public Wi-Fi systems are susceptible to that. So there is no guarantee that you can be free from this attack. This is why ARP is most of the time not used whenever you can afford to prevent it from happening. In particular, in enterprise networks, if you buy Cisco equipment, and I guess Juniper is the same, in enterprise networks, the boxes that are the switches, for example, that are the Ethernet boxes to which you connect, or the routers themselves, they will try to prevent ARP from happening by keeping a table of all the MAC addresses that corresponds to given IP addresses. And this will be particularly easy to do if we use DHCP, that we will see in a second. DHCP is a method by which we allocate the IP addresses. So if we have a server that can allocate the IP addresses to some given machines that have known MAC addresses, because with DHCP you will need to reveal your MAC address, then this mapping is known to that server. So instead of using ARP that asks everyone, tell me who has this address, we directly get that information from that server and put it everywhere where it's required. For example, one place where it's required is in the switch, the Ethernet switch. When it sees a broadcast, when you send an ARP request or a neighbor solicitation, that is broadcast or multicast to everyone, then the switch will violate the TCP-IP architecture if you want. We'll look inside the packet, we'll say, oh, this is an ARP packet, I refuse to broadcast it, but I will try to see if it's if I have a correct answer to the query that's asking it. So if the machine that you're trying to reach has received its address from DHCP, the information is in the DHCP table that has communicated with the switch the same information. So the switch will have this information, and you can do all the ARP you want. It will be blocked. So this is typically deployed in enterprise networks and prevents this spoofing. It also prevents another thing, which is sometimes called a broadcast storm. With ARP, we do a broadcast, which means we send a packet to everyone. Now, if there is a bug in one system that for some reason, for example, it's trying to boot, and at some point when it boots, it needs to find a MAC address, and then it sends a broadcast and hangs and reboots again. So it may be flooding the network with broadcasts. There were in the past evidences of what is called broadcast avalanche or storms that are compound effects that were, for example, having a host that is wrongly configured and responds to broadcast address with another broadcast. So that if you manage to instill one query, that would cause a succession of broadcast address, and every broadcast address would cause other machines to respond with a broadcast. Now, if you send broadcast messages, if you want to do a denial of service attack on a network, broadcast is a very powerful way to do it, because you send the packets to everyone. So ARPs have this reputation of lending themselves to broadcast storms that may bring networks down. So enterprise networks will try to avoid them. Your Wi-Fi at home and the access points you may find here and there probably don't do that. Another small question to keep you fit. Here I'm assuming traffic that goes from this machine, M1. M1 is its MAC address, P.H1 is its IP address, and it sends a packet to M3, which is Q.H1. And I'm asking, what do you think could happen among the proposed options? I close in 5 seconds. The correct answer is B. When this guy boots, it will need to hopefully it is configured with the default router that must be addressed P.1. In many networks, the default router is the subnet .1. That's the case at EPFL, for example. So here, it will need to find, therefore, the MAC address of P.1. Here. Right. I've spoken of automatic host configuration. That's a fairly easy topic that we will go through now. The non-easy thing is that there's an avalanche of variants in the case of IPv6. But the key word is DHCP. So a drawback of IP is that you need some configuration. You cannot simply take two machines, a printer and a computer, connect them together, have TCP-IP printing, and all the spooler software runs on TCP-IP, and hope it works. You need somehow to configure things, in particular, those pieces of information, IP address of this interface, the mask, the IP address of the default router, which is called the default gateway, and probably also a DNS server, because you will probably send to the printer by using the printer name and not an IP address. I said you need to configure this. If you don't configure, there are ways to make it work, in particular with what is called auto-configuration. That is, in some sense, automatically configuring those elements here. So you need this to be configured for something to work. At the beginning, it was a drawback for IP. Other systems like AppleTalk, that was one of the very superior systems at that time, did not have this problem. You had what was called a Macintosh office, dentist's office, because dentists were supposed to be requiring technology, but not having the knowledge to make it work. So they needed to connect the X-ray machine to the database server and the computer to the printer. And if they bought all Apple stuff, you connect everything with AppleTalk wires, and it works. No knowledge of IP addresses, mask, whatever. It just works. Right? The way it worked is that AppleTalk uses machine names as replacement for IP addresses. So each machine has a name. You need to give it a name. If you don't give it, it will find its own way to find a name with a cryptic series of characters. And then it uses protocols like ARP to discover who has that name by extensive use of broadcasts. This is obsolete today. Nobody uses AppleTalk, at least in this form. We use IP instead. But that required solving this problem of configuration here. Configuration today is solved by DHCP. DHCP was invented for IPv6 in the 90s. Before that, you needed to configure manually, like we do sometimes in the lab, all those fields. You go to the fields and you give the values. But today, by default, you tick the box, get an address automatically. And the automatic thing is dynamic host configuration. That assumes that there is somewhere what is called a DHCP server, which we can view as an application layer protocol, DHCP, but a special application, one that is for the configuration of the network itself. So you need a server, a DHCP server, for DHCP to work. Very often you have it without you knowing that you have it. For example, what is called your ADSL box or your Wi-Fi router very often is a router, also perhaps a Wi-Fi base station, but might be also is a NAT, like we've seen an hour ago, but typically is also a DHCP server. A DHCP server is something that has a table with rules to allocate IP addresses to different elements of the network. If you have a very simple network, then it will need only to be configured with one network prefix. If you have a complex network like ITPFL, the system managers need to design in the DHCP server the addressing plan of EPFL. So which subnet will have which prefix. All of this is written in an application that downloads a DHCP table in the DHCP server. Now, in the simplest case, the DHCP server is in your LAN. In the more complex case, there is what is called a DHCP relay in your LAN. What is a DHCP relay? A DHCP relay is like a meta box or meta function. Meta because it works before IP works. It is something that is often called a router function. So typically, it's some software you add to a router. But it's not a router function in the sense it's not forwarding packets based on IP headers. It is an application layer gateway where the application is DHCP. It is something that receives DHCP queries and responses, looks at the inside of them, and makes a decision based on them. The simplest decision here being to forward it. Let's see what happens. I have my PC that boots in a network. If it's configured to do automatic address allocation, it will send a query, which is called a DHCP discover, which is, the goal is to say, here I am, and I would like to have an IP address. So it will contain things like my MAC address, the MAC address of this guy here. It will be sent to the UDP port for DHCP. So we see that DHCP is an internet application. It has a UDP port. So the UDP port being 67. And to an IP destination address, which is, what IP destination address can it be? Well, with IPv4, as usual, we don't know whom we're talking to because we have no information. We're not configured yet, so we broadcast. So we send to everyone. And the source address will be 0, absence of address here. So it's a very strange packet that is broadcast with source 0. Of course, when a packet like this is received by a router, what do you think that will happen? If we are a bit short-sighted, we say, well, a router should do its routing job. So we see a packet that means broadcast means everywhere, right? It means the whole world. In theory, we should send only to the subnet broadcast, but we don't know the subnet mask, so it's impossible. So that's all we can do. But of course, one rule of a routers is you never send a packet to the whole world. So if a router receives a packet that has destination universal broadcast, the router will drop the packet. Will say, thank you very much, but I refuse to do that. Otherwise, it will be very easy to bring the internet down. Each of you in this room does a little program that sends a packet to all routers, to everyone, and the whole internet would be flooded. Of course, it could happen once, and then everybody would realize it's stupid, so it would be dropped. So, of course, this packet is never forwarded by any router. Plus, it probably has a TTL of 1, as we will see in a second what it means. Here, it's not forwarded by the router, but in the box called a router, there is another object called the DHCP relay. And this one will see the packet. So the packet is sent to everyone. So the router has two jobs. It is a host, and it is a router. As a router, it forwards packets for others. But as a host, it says, oh, is this packet for me? And the answer here is yes, because this packet is broadcast. Broadcast inside the LAN is admitted, is acceptable. So if this packet comes from within the LAN, inside the LAN I receive a packet sent to everyone. It can be an ARP, things of that kind. So I accept it. But of course, I accept it as a host, which means I can do something with it if I have an application program that's willing to do something with it. That's the case if we have, inside this box, a DHCP relay that listens to port 67. If that's the case, then it will receive this message. So the message is, there is someone on my interface, I don't know, ETH1, that would like to have an IP address. Now, I am a DHCP relay. I am configured. I'm part of the EPFL network. I have the IP address of the DHCP server. I will forward this message over the rest of the network to the DHCP server. And I will copy all this information. I will copy other information. I will copy in particular the interface on which it came. Now, because I know the interface on which it came, I could know, in fact, here what is the prefix, but here I'm just a relay, so I'm a stupid machine, I relay. So the DHCP server will respond by this is IPv6, will respond by sending a message back to the relay router. The DHCP server cannot talk to this machine directly because this one doesn't have an IP address and it's not on the same LAN. But it can talk to the relay router, and in the response there will be all the configuration information, which is in particular which IP address this guy should use. And perhaps also things like IP address of a DNS server. Now this guy will receive the response. Now, of course, it has remembered the, I'm not even sure if it needs to remember. In the response, it will have all information. In particular, it will have the interface on which to send it and the MAC address, so it can send it as a DHCP packet to an IPv4 broadcast address and to the MAC address that is given here. So even if it's broadcast, the fact that it is MAC address, or I'm not sure whether it's in broadcast or the 0 address, by means of the MAC address, it will reach, in principle, only this client, which will now have the information. Question?
I have a question, because as I understand, this discover packet is sent in a tenet frame.
In a?
A tenet frame has a source address, so why put it again in the discover message?
Say again your question?
So the discover message is in a tenet frame, right?
What do you mean by attempt way?
Ethernet frame.
Ethernet frame. Yes, it's an Ethernet frame. Yes, it is here encapsulated in Ethernet. And of course, now the DHCP relay is an application. it will not see the Ethernet frame and all that stuff, right? So this is the method by which, with a single DHCP server for a whole enterprise, you are able to reach all the clients that still don't have IP addresses, but you need for that to put a DHCP relay function in all routers. With DHCP, with IPv6, it's the same, but as usual, it's much more complicated. I will skip some of the details. The main complication is that, as usual, we try to avoid broadcast addresses by having a combination of special addresses that are formally multicast addresses. Sorry, I should mention now. In IPv6, there is another method which is called Autoconfiguration. It was inspired by the requirement to do the same as AppleTalk did. You open from the boxes a number of machines, and you would like that they're all able to get their addresses automatically. Well, the idea is very simple. How you imitate what AppleTalk did, but it's not rocket science. It's very simple. The problem is every host should have an IP address. So how can you have an IP address? Well, in IPv4, what you do, if you implement auto-configuration, which I believe Windows operating systems do, if they connect and there is no DHCP, no manual configuration, they will still try to get something, and they will give to themselves an IP address. How do you give to yourself an IP address? In IPv4, it's difficult because there are not so many addresses, but you try one address, and then you do what is called an address duplication test. The problem that could arise is someone else has the same address as you. But what you do is you broadcast in the local area network a reverse ARP, if you want, an ARP response where you're saying, hey, here I am, and I have this address. And you do it a number of times. If nobody complains, then you think you have this address, it's correct, and you keep it. This is how auto-configuration is done, typically. It works or it doesn't work. It works if the others who have the same address as you are not sleeping, which are perhaps not the case for smartphones, for example. If they have very aggressive sleep management systems. So if nothing happens, the system goes to sleep. So if a query comes to see, do you have this address? Your machine will say, no, I don't. But someone else has the same. And when they will both wake up, there will be conflicts. That happens. That's a cause for misfunctioning. In IPv6, it's less likely to happen because instead of broadcast, we send to specific addresses that are based on the MAC address, a locally derived MAC address. And a locally derived host part, where the idea is that in IPv6, you have lots of space in the address. So you could put in the host part your MAC address. In IPv4, we count the MAC address is 48-bit, IPv4 is 32-bit. But IPv4 host part is in the rule 64 bits. So we can put the 48 bits of the MAC address, and the MAC address is supposed to be unique unless some manufacturers are not correct. So you can do address auto-configuration simply by putting in the host part your own MAC address. This is what is done in IPv6, and it's called SLAG. Now it's there are, as usual, many tricky details. How do you map 48 bits into 64? It would be very easy to add zeros at the beginning, but it's a bit more complicated, and it's explained here. As a result, the host part is typically, when you do the auto-configuration, is typically your MAC address. And this was the state of things 15 years ago. This was how IPv6 was working. Then some people voiced a concern about privacy. If you use that a lot, that means whenever you communicate, wherever you are, your IP address will change depending where you are. But if you use the same device, your MAC address will always be the same. So it will be visible who you are from your IP address. So 15 years ago, people were worried about that, so they invented another mechanism where we change the address randomly. So you will start like this, but you will also allocate to yourself a random address. Once you have one address that works, you will allocate to yourself another address, and there is a procedure to change addresses. The procedure is that when you have a new address, of course, once you have an address, you can get all the configuration information, so you're in business. The only problem is if you have an established TCP connection, you're transferring a video from YouTube, and that takes 1 hour. And if in the middle of this you change your IP address, the connection will be broken. Which probably is okay, you restart. But if you don't want the connection to be broken, you want a smarter thing. So what is done is that whenever a new address is allocated, it becomes the preferred address, and the old address becomes deprecated. And deprecated addresses are still valid. They can be used to carry traffic, but you can never start new flows. So if you use UDP, you will not use this address. And if you use TCP, when you start a TCP exchange, when you start what is called a TCP connection, you are not allowed to use this address. And after some time, this address will expire. What's the net effect of that? Well, the net effect is that with IPv6, it can be that the machine has several addresses. It typically has several addresses, one that has acquired by auto-configuration, which is typically valid only in this local area network. And when it has done its auto-configuration, it can talk to DHCP server to get more information, or to finalize the end of the auto-configuration and get its own prefix. I will skip this and skip all of this, and perhaps I will terminate okay, I think that's a sign that we need to close for here. So that's all for today. See you tomorrow at 11:15 sharp.